Extra exercise 2. Consider a track ABC situated in a vertical plane as shown in the adjacent document. The track ABC is formed of two parts, an inclined part AB, a horizontal part BC of length BC equals 2 meters. A solid S considered as a particle of mass m equals 0.1 kilograms is released from rest from point A. The solid S is submitted to a friction force of constant magnitude F only along the path BC. The horizontal plane passing through BC is taken as a reference level for gravitational potential energy, given that the height of point A relative to the reference level is HA equal 1.5 meters and G equals 10 meters per second squared. So at point A, calculate the value of the kinetic energy of the solid S. We are given that it started from rest, released from rest from point A. So kinetic energy at A is half mv squared, half times 0.1 times 0 squared. Here the mass was given to be 0.1 kilograms in SI unit, so we substitute it as it is, 0.1 times 0 squared, so this is 0 joules. Now calculate the value of the gravitational potential energy at A of the system. So we are given the height at A and the rule says that mg gravitational potential energy is m times g times HA, so 0.1 times 10 times 1.5 meter. All are given in the SI unit, so it's equal to 1.5 joule. Now deduce the value of the mechanical energy at A of the system as Earth. So having kinetic energy at this position, having gravitational potential energy, we say that mechanical energy at A is equal to kinetic energy at A plus potential energy at A, which is equal to 0 plus 1.5, yani 1.5 joules. Now the solid S reaches point B with speed VB that's unknown till now. So the mechanical energy of the system as Earth is conserved between A and BY. We were given that the friction is only applied on S along BC, so BC is the rough, however AB is smooth. So that's why we consider AB as frictionless and the mechanical energy of S as it moves from A to B is conserved. So why is it conserved? Mechanical energy is conserved between A and B since there is no friction. Now deduce the value of the mechanical energy at B of the system as Earth at point B. If you thought about writing mechanical energy at B equals mechanical energy equal kinetic energy at B plus GPE at B, you won't be able to find the answer because simply you cannot find the kinetic energy at B by till now because VB is unknown. So the question is deduce. This means that you have to make use of the conservation of mechanical energy. Mechanical energy at A equals mechanical energy at B equals 1.5 joules due to conservation of mechanical energy. A was calculated in the previous part. Now determine the speed VB. To find the speed, we need the kinetic energy. And to find the kinetic energy, we have to relate it to the mechanical energy. So we say that mechanical energy at B is kinetic energy at B plus GPE at B. However, GPE at B is 0 joules since B is on the reference level of the gravitational potential energy. It's along BC. So we said that BC is the reference and B belongs to this reference. So that's why we say that mechanical energy at B is equal to half mvp squared plus 0. You should substitute correctly here because you mentioned kinetic energy first, so you have to write first half mvp squared, then plus 0. So this was typed by mistake here. Now, so VB is equal to radical 2 mechanical energy at B over M. If you do here the calculations, VB squared is multiplied by M over 2, so you multiply both sides by the reciprocal, it becomes 2 mechanical energy over M equal VB squared, but we want VB, so we have to do square root. So VB, also take the square root. VB is equal radical to mechanical energy at B over M, 2 times 1.5 over 0.1, this is radical 30, 5.5 meter per second. Now the solid S continues its motion along BC and reaches point C with 0 speed, BC equals 0. Calculate the mechanical energy at C of the system at point C. The mechanical energy at C is kinetic energy at C plus potential energy at C. But potential energy at C is 0 since C is on the reference level of the gravitational potential energy. Then now we have that, and the kinetic energy at C is 0 joules since Vc equals 0 meter per second. This was given. So mechanical energy at C is equal 0 plus 0 is equal to 0 joules. This means that S starts moving from B with energy, and then on its pathway, on its path to reach C, it loses its mechanical energy until it loses it totally and stops there. This is due to friction for sure. So calculate F knowing that mechanical energy at B minus mechanical energy at C is equal to plus F times B. So if you go back to the course, we defined the difference or the variation in the mechanical energy as the final mechanical energy minus the initial mechanical energy. And we said due to friction, so this rule is true when there is a friction. So, and due to friction, the system loses energy. So the final mechanical energy is less than the initial. For example, if the final is a 3 and the initial is 5, so we will get this difference is negative. That's why here we write equal minus the magnitude of the friction times the distance covered. Okay, so it's equal actually to the work done by the friction force. So the difference here in the mechanical energy is equal to the work done by the friction force. Now here you are given it in an opposite way. They gave you, mechanical energy initial minus final. For the phase BC here, B is the initial position and C is the final. So because initial is greater than final, so the difference here will be positive, and that's why we write it's equal to plus F times BC. So if it's given this way, you have to apply it this way. If it's not given, and you know that you need to make use of this here and here, then you have to abide by the given rule. Final minus initial equal minus F times C. Doing the substitutions now, 1.5 minus 0 over 2, this is 0.75 in Newton.